Hello, and welcome to today's ACM Tech Talk. This webcast is part of ACM's commitment to lifelong learning and professional development, serving a global membership of nearly 100,000 computing professionals and students. My name is Travis Humble, Editor-in-Chief of the Transactions on Quantum Computing, a new journal from the ACM that addresses the rapidly growing field of topics in quantum computing and quantum information science. I'm also Deputy Director of the Quantum Science Center at Oak Ridge National Laboratory, a Department of Energy National Quantum Information Science Research Center. To learn more about my background, check out the bio window on your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here is some more information. ACM offers educational and professional development resources that bolster the skills and enhance career opportunities. Our members stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources available at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations, staying competitive in a global environment. This includes providing timely computing information published by the ACM, including transactions on quantum computing, access to the ACM Digital Library, the world's most comprehensive database of computing literature, many international conferences that draw leading experts from a broad spectrum of computing topics, and support for education and research, including curriculum development, teacher training, the ACM Turing Prize, and ACM Prize in Computing Awards. And of course, the updated ACM Code of Ethics, which provides a collection of principles and guidelines designed to help our computing professionals make ethically responsible decisions. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First, the slides during the talk will advance automatically. On the bottom panel, you will find some additional widgets and resources. If you are experiencing any problems with the slides or audio, press the F5 key in the Windows operating system, or the Command R key if you're on a Mac, or on a mobile device, try refreshing your browser. Of course, you can always close and relaunch the presentation. To control the volume, adjust the master volume on your computer. If you have any questions during this talk, please type them in the Q&A box at any time and click the Submit button. At the end, I'll organize the questions and present them to Stephanie at the end of her presentation. This session is being recorded and will be archived. You'll receive an automatic email notification when it becomes available. You can check learning.acm.org for any updates. At the end of the presentation, you'll also see a survey on your screen. If you can, please take a few minutes to fill it out and help us improve Tech Talk. You may also open the link to the survey anytime from the resource window. You can, of course, use Facebook and Twitter widgets on the bottom of the panel to share the presentation link with your friends. If you tweet comments and questions, please use the hashtag #ACMLearning. We'll be watching for your tweets. We also have an opportunity, a community discourse page to continue the discussion after the webcast. Now, today's presentation is Quantum Networks, from a physics experiment to a quantum network system by Stephanie Wehner. Stephanie Wehner is the Antoni van Leeuwenhoek Professor and Roadmap Leader for Quantum Internet and Network Computing at QTech in Delft University of Technology. Her goal is to understand the world of small particles using the laws of quantum mechanics in order to construct better networks and computers. Stephanie has written numerous scientific articles in both physics and computer science, and she is one of the founders of Qcrypt, which has become the largest conference in quantum cryptography. At present, Stephanie serves as the coordinator of the European Quantum Internet Alliance. And from 2010 to 2014, her research group was located at the Center for Quantum Technologies at the National University of Singapore. And previously, she was a postdoctoral scholar at the California Institute of Technology. And in a former life, she worked as a professional hacker in industry. Without further ado, Stephanie, welcome to ACM Tech Talk. Please take it away.
Thanks very much for the introduction, and thanks to all of you for joining this talk on quantum networks. In this talk, I want to take a look on how we can, from a computer science perspective, take quantum networks from a physics experiment to a real network system. So what is the ultimate goal of constructing a quantum network? Is, as I like to say, to create entanglement for everyone and eventually to connect quantum processors anywhere on Earth. So you've probably heard about quantum of being different to classical computing in the sense that the objective of quantum communication is not to send zeros and ones, so classical bits, but actually quantum bits, which in a certain sense can be 0 and 1 at the same time. So before giving you an introduction to quantum networks, you may be wondering, why are we actually looking to construct quantum networks in the first place? Quantum networks have many applications. Probably the most famous one is secure communication. Quantum networks allow a sender and receiver anywhere in the network to exchange an encryption key with security that cannot be broken even by a quantum computer. However, quantum networks are useful for all kinds of other things. For example, to perform secure quantum computing in the cloud. Here, the objective is to use a very simple quantum device, a quantum terminal if you want, to get access to a remote quantum computer and perform computations, for example, simulations of new proprietary materials, in such a way that the server can actually not learn what the material design is that you want to perform the simulation on. Quantum networks have all kinds of other applications, for example, in the domain of improved clock synchronization, position verification, and even online games. Of course, just like in the classical domain, networks can not only be used to solve communication tasks, but also perform a path to a scalable quantum computer by wiring together small quantum computers to form one more powerful quantum computing cluster. So you may be wondering, what is it about qubits, or in fact, this concept known as quantum entanglement, that enables all these fantastic applications? So in order to think about that, there's essentially two properties of entanglement that are relevant for enabling these applications. So let me explain what these two concepts are to give you some intuition of what quantum networks are good for. So first of all, entanglement enables stronger correlations between different sites. So I like to sometimes call this as maximum coordination. An example of such strong correlations is that if I have a qubit here in The Hague, you have a qubit in your office or your home right now, and we've used the quantum network to entangle these two qubits, then if I make a measurement on my qubit here, there exists a measurement that you can make that gives you exactly the same outcome. And this actually works for any measurement that we're going to make. So if I make a measurement that says, hey qubit, are you pointing left or right? And say I get the answer left, then you make your measurement, you also get left. If I get right, you also get right. And this works even if the answer was not determined ahead of time, and it works in a sense instantaneously without the need for further communication. So this makes it possible for a quantum network to solve certain tasks that require coordination more efficiently than a classical network. The second property of quantum entanglement is that it's inherently private. Because of course you may be wondering, given that we have this beautiful coordination, can we share that? Can we involve, for example, a third party and be just as coordinated? So the answer to that is actually no. If my qubit is maximally entangled with your qubit, then it's actually physically impossible for anything else to have any share of that entanglement. So you can think that entanglement thus forms a private connection that by the laws of physics, nothing else can have any part of. And this second property is what makes quantum communication so suitable for solving problems that require security. For example, secure communication. So before talking a little bit about also the computer science challenges in this domain, let's have a look at a little bit of a cartoon of what actually are the elements that appear in a quantum network. So essentially, you can imagine quantum networks to look very differently to classical networks as we know today, except that everything is quantum. Of course, we will have what we like to call end nodes. Essentially, this is, say, your laptop or your phone that connects to the network, a host on which you can run applications to make the network useful. So such end nodes in a quantum network can be very simple photonic devices that are capable only of preparing and measuring a single qubit at a time. But there may also be, in the future, large, powerful quantum computers that are capable of storing and manipulating qubits. In order to bridge long distances, we will eventually need to construct a quantum repeater. And I'll say a little bit more later on how one thinks this might once work in the future. Of course, just like in a classical network, we also need to send, actually, in this case, qubits or to produce entanglement between two different sites. And this can be done over normal optical fibers, as they are also used today. Right. So now that we have some ideas of sort of what happens in this network, let me maybe say sort of what we need from that network in order to implement certain applications. So if you're curious to learn more about what quantum network can do and also when it can do that, we've tried to classify, in fact, the requirements of quantum networks by putting forward functionality-driven stages of a quantum internet. So this takes a purely application-level perspective and asks the question, how powerful does a quantum network be in order for us to realize certain applications? So this starts from very simple prepare and measure networks, where the end nodes can only prepare and measure single qubits, all the way to networks in which the end nodes may be full-blown quantum computers and anything in between. So depending on what stage of development a network can reach, more and more applications become possible. So if you're curious, you can read more about that later. And it presents a challenge both to, of course, say hardware development in order to build ever more powerful quantum networks and quantum devices. But it's maybe also a question for you, if you're interested actually in developing quantum network applications, to lower the requirement of these protocols. So say I want to perform clock synchronization. Do I really need a quantum network where the end nodes are fault-tolerant small quantum processors? Maybe we can do that with much simpler devices, reducing both the requirements on the end nodes connected and of the network itself. So you may be asking, where are we right now? Because, of course, quantum networks don't exist yet. They are currently a beautiful idea that we're working very hard to make reality. Quantum communication is, however, in fact, already industrially available at short distances for very simple applications for users which are communicating point to point. So quantum cryptography, meaning secure communication, is actually something that you can buy today. Several commercial devices exist that you can acquire that can perform quantum communication for the single use purpose of performing quantum cryptography at short distances, and short meaning roughly 100 kilometers in fiber. In the lab, people have, of course, gone beyond that a little bit, but the grand challenges actually are that we want to increase the distance and also implement more things in QK. So if you've been Googling around a little bit of quantum communication, then people have, of course, managed to do that at longer distances. For example, people have, from space, produced entanglement over a distance of 1,200 kilometers from a satellite. So it's a satellite in space that produces two entangled qubits and sends one to the left and one to the right on the ground. So this is great. But of course, it's not quite fast enough for us to do full-blown secure communication. And of course, also we would like to eventually connect other users on the ground, which requires also the use of quantum memory. So quantum communication on the ground, entangling, in fact, quantum processes of quantum memories is much less advanced. We have a few years ago by now actually entangled two quantum processors, or two little quantum computers if you want, at a distance of 1.3 kilometers on Delft campus. So that's of course not very far yet, but we're working hard to extend that distance. If you're curious to read more about this, there have been some recent results to entangle two quantum memories in the same lab. So they're not at a specific physical distance, but just connected over a longer fiber coil. And there's also some nice work to connect a sort of a great entanglement between one quantum computer and a traveling photon over a longer distance. So you may be asking, well, before this talk, I tried to Google quantum networks, and I discovered that there's some very large ones, for example, in Tokyo or in China. So what's up with this? So the main difference actually between the quantum networks that we're really looking to build and the quantum networks that may appear to bridge long distances is that we're really aiming for end-to-end transmission of qubits. And that's important because it also enables, for example, end-to-end security of quantum key distribution. So what's happening in the networks that you maybe found online is that we actually don't have end-to-end quantum communication yet. Instead, it works a little bit like what you see on the slide. Let's say that Alice and Bob are too far away that they can directly send qubits to each other. Say they're maybe 500 kilometers apart. But maybe they have a friend, Charlie, who sits in the middle. So what happens in these networks right now, that instead of having end-to-end quantum communication, Alice and Charlie send qubits to each other, and Charlie and Bob send qubits to each other. And they use that to produce, using QKD, one encryption key between Alice and Charlie, and a separate one between Charlie and Bob. So this, of course, enables end-to-end secure communication between Alice and Bob, as long as they trust Charlie. But of course, Charlie can, in principle, know everything. So for example, on one of the networks that you see here, there's actually 32 of these points at which you may intercept the key. So going forward, we wanted to overcome that problem, and you can think that actually in the construction of future quantum networks, there's three challenges that you can see on this axis. One of them is to increase the distance. So we want to produce end-to-end entanglement and end-to-end transmission of qubits. We want to increase the functionality. So we don't only try to build this so we can do secure communication, but we're interested in all these other applications as well. And the third one is what I sometimes like to call accessibility, in the sense that we're interested actually in making this technology available as early as possible to as many users as possible. And this means an effort also to make initial devices or simple devices smaller and faster and cheaper, so that more people can make use of it. So before going into quantum networks, I also want to tell you a little bit what we're doing at QTech, where our effort is actually to create the quantum networks of the future, going beyond trusted repeaters to end-to-end quantum communication. So we're currently working on a link between two quantum processors, so two little quantum computers, one in Delft and in The Hague. And the reason why we're doing that is, of course, to bridge longer distances in the future. So you can see a little bit why this can work later in this talk. But also, of course, to bring our technology actually one step further away from a physics experiment to an actual network system that can also be deployed in more places in the future. So indeed, our plans are also to actually expand this network beyond this point-to-point situation. So you may be asking, so why is she obsessing all the time about these long distances? Why is it actually so difficult to send qubits over long distances? And there's actually two reasons for that arise from the fact that quantum communication behaves very differently than classical communication. And one of that is actually a fundamental reason. Namely, we cannot copy qubits. This is very powerful because it is actually what also enables quantum security. If I send you a qubit, no one can make a copy of it. But at the same time, it's also a little bit annoying because if a qubit gets lost in transmission, then there's no way to resend it. The second reason is actually not a fundamental one, but a technological reason. On paper, quantum networks are very easy. You're just going to bury a quantum computer in the ground every 10 kilometers. We're going to do forward error correction. and then we have quantum networks. But of course, reality is not quite so easy. So the second technical challenge is to realize quantum networks with as simple hardware as possible. And this is actually something that computer science can make an important contribution to, as we'll see a little bit later in this talk. So the objective here is to try, using smart methods, to mitigate the fact that quantum memories have short lifetimes and it's difficult to manipulate very many qubits at once. In order to do that, it's also important to understand that quantum entanglement, so two connected qubits in a way, works very differently than how we communicate classically. So in classical networks, a lot of information is sent by forward communication. I send a number of bits to you, a number of physical signals from A to B. But entanglement is even at the fundamental physical layer of quantum networking already an inherently connected element. It can only be used if I know who has the other end, and also the receiver can only make meaningful use of this entanglement if he knows who is the sender who holds the other qubit of this entanglement. Entanglement is very important for quantum applications, and I hope you got a little bit of intuition why this is before. But entanglement is actually also itself an enabler in trying to bridge long distances and to send qubits. And I'll explain to you a little bit why this is, and then we'll try and do a little bit of resource counting on how computer science is, I think, necessary and important in order to be able to control such networks of the future. So let's imagine that we've already produced entanglement between the sender and the receiver, indicated by these purple qubits connected by this wiggly line. So a process known as quantum teleportation allows us to send a data qubit, here the yellow qubit, using quantum entanglement. So this means that we will first produce the entanglement, then we're going to make a measurement on our data qubit and the entanglement to transfer the data qubit to the receiver. Let's think a little bit about what this actually means for the design and the control of such networks. So I said that, in fact, qubits cannot be copied. So if we had tried to send the data qubit directly and it got lost, then we forever lost our data qubit. So repetition is not a way to overcome errors by just sending data qubits again and again. But you can see now that what we've done here, by actually sending qubits not directly, but sending them using teleportation, that repetition does again become a means to overcome errors. We will first try and produce the entanglement, and that is something that we can try many, many times. And once we've confirmed that we have entanglement between the sender and receiver, then we can reliably send the data qubit without any fear of it getting lost. So teleportation sounds very fantastic. And you may be saying, maybe I need to know a lot of physics in order to maybe participate in this research. I think from a computer science perspective, it is often enough to approach this from a purely resource perspective. So yes, we needed to produce the entanglement to send the qubit. But the resource counting that we just need to be aware of is that actually this process consumes the entanglement, meaning that we can use it only once. And that also will require 2 bits of forward communication from the sender to the receiver in order to perform this quantum teleportation process. So make entanglement, make a measurement, 2 bits of forward communication to transfer the qubit. So I already said a little bit some time ago that entanglement is actually also useful to bridge long distances. And this is, in fact, one of the essential ideas that goes into building a quantum repeater. And now that we understand teleportation, I can maybe also explain to you what that idea exactly is. So let's imagine that we have 2 nodes, Alice and Bob, here on the slides, by the nodes on the left and the nodes on the right, with a single purple qubit inside. Let's say that they're actually too far apart to perform quantum communication directly. But in the middle, in this blue box, we have a quantum repeater. So the essential concept is that actually the left node, say Alice, will produce entanglement with the repeater. The right node will produce entanglement with the repeater. And we will then use this to produce end-to-end entanglement. And in Setchen, this is just teleportation. So if you imagine now this yellow qubit being the data qubit, we are going to use teleportation to transfer it. This means that on the repeater, we make a measurement. And based on the outcome of this measurement, we can then produce entanglement end-to-end. So this may seem pretty fantastic, but again, if we want to think about sort of maybe scheduling or designing control protocols from a computer science perspective, I think it is enough to understand some basic resource facts about this process. First, it is sort of clear that it requires some amount of timing coordination, meaning that we can only make the measurement at the repeater in the middle if we actually have entanglement both to the left and the right at the same time. So this means that we require either tight timing coordination, or we need to have a quantum memory at the midpoint, so we can actually wait until both qubits are being produced. I've already said that quantum teleportation requires actually classical communication. And from a research perspective, it is important to understand that this process of entanglement swapping, producing entanglement via this node in the middle, requires actually classical communication from the midpoint, the repeater, to the endpoints. And that, of course, requires time. And that's important to understand in the design of such control protocols, because quantum memories have short lifetimes, and that means that waiting for classical messages is something that we're trying to minimize. And of course, as I just said, teleportation consumes the entanglement. So we cannot just, keep doing this magically. But if we want to have end-to-end entanglement, we need to repeat this process of producing entanglement with a middle. So many systems are proposed actually that can perform this form of entanglement swapping, as it's called. And I'll just give you one example here that we also have in Delft. So an example of such quantum hardware, for example, is a system called nitrogen vacancy centers in diamonds. And again, this may look like a fantastic physical system, but again, from a computer science perspective, I think it's sufficient to understand that it is basically a small quantum computer of several qubits. And the important distinction of these qubits is that some of these qubits are communication qubits, which is actually the electron spin in this nitrogen vacancy center, and some of them are storage qubits. And the only distinction between them is that communication qubits can talk to the outside world, meaning we can produce entanglement between such a qubit and the traveling photon. And the storage qubits can, unquote, only be used to store and perform quantum gates on these qubits. So I mention it again because if you're a computer scientist and you're thinking about designing control protocols, it's important to understand that the number of communication qubits limits the number of simultaneous entanglement that you can produce, entanglement that you can produce at the same time with your neighboring nodes. So how does such physical entanglement generation work? So again, I'm trying to limit myself actually to understanding the resource constraints involved in that. So how entanglement is produced is that one shines a laser on our communication qubits at these two endpoints, producing entanglement between an endpoint and the traveling photon. So if you remember that earlier picture of the quantum repeater, so these little diamonds, the endpoints, are the nodes, here having the purple qubits, to a middle station, here being the light blue box. So I have a video to explain a little bit more how entanglement is produced. So remember this entanglement swapping process. We first produce entanglement of the endpoints to the midpoints, and then we make a measurement. How this works is that one shines a laser on the communication qubits. We produce entanglement between the communication qubits and the physical traveling photon, which traveling to this middle station here involving the beam splitter, the plate, and these two detectors. And if detection is successful, we've now produced entanglement for this wire between the blue qubits at the end. So the question is a little bit, can I work with this without understanding much physics? And I'm trying to actually motivate you to get engaged with this because I think we need more computer science work. So the answer to this question, can I work with this physics, is to some extent yes. So I've already maybe given you some basic resource constraints that make this possible. And I want to give you just one little example, actually, of work that we've done recently of a link layer protocol for quantum networks. So just like a network stack in classical networks, we've thought about a stack for quantum networks. And let me explain a little bit what this actually means. So a simple division here is very similar to what we see classically. So physical layer, link layer, network layer, transport, and application. Meaning here, something very similar to what we have in the classical domain. So the physical layer is formed by the quantum device layer. So this is really sort of where the physics come in, where actually we talk about qubits and physical devices and they control them. The second step, the link layer, is what we take, it's just an analogy to what link layer means in classical networking, to mean entanglement generation on a link. So we have two directly connected nodes and we produce entanglement between them. The network layer means that we're going to produce entanglement via an intermediary node. And the transport layer is end-to-end qubit delivery. And of course, at some point, we'll talk about application protocols. So we've done further work than the link layer now, but to keep this talk a little bit simple, I really focus on this part now, namely how we can go from the simple sort of physics experiments that I've just told you, where we shine laser on diamonds, to a more computer science perspective by talking about a link layer protocol that performs an entanglement generation service. So instead of talking about actually physical diamonds, I want to think now about the quantum entanglement generation protocol of the link layer. So the service that we defined to provide to a higher service is that higher layer can say, hey, I want to produce some entanglement, create. And eventually, the link layer is responsible for robust entanglement generation, meaning that we'll keep trying and trying to produce entanglement until eventually it may succeed or experience failure or timeout and say, okay, I've produced desired entanglement for you. So for example, if you think about the example of wanting to teleport the data qubit, it would mean that we would first ask the link layer to produce entanglement for us, and once the entanglement is ready, we can then perform the teleportation. So if you want to go out and design the quantum network protocols, it's of course a little bit useful to think about what are the performance metrics by which we're going to judge such protocols. So some of these, of course, are standard metrics. So meaning what we also see in classical networking, namely latency, throughput, and for example, fairness. So latency, here meaning that the time between the request for entanglement and actually getting a pair, so meaning a pair of entangled qubits delivered. The throughput is just the number of entangled pairs per second. And the fairness, one can think about the difference in the performance metrics depending on which node in the network requests such entanglement. So you know probably a lot more than I do, in fact, about maximizing these standard metrics in a classical network. But the challenge actually in designing such protocols, apart from the fact that entanglement, of course, is an inherently connected element and many other challenges, is that we want to balance these standard performance metrics with another metric, namely the fidelity, so the quality of the entanglement generated. So if you come from classical networking, you may be saying the quality of the entanglement, why do I worry about that? In classical networking, after all the errors are typically eliminated before you bring it up to the application layer, using error correction, for example. So in essence, it's important to understand of designing quantum network protocols that the entanglement that we want to deliver to the application does actually not need to be fully corrected. So also imperfect entanglement is something actually that we are totally happy with, for example, to perform secure communication. So that makes an important difference on what we require actually from such communication protocols. So the reason why also imperfect entanglement is fine, to give you an intuition, is because we will then actually use classical methods in order to overcome these imperfections, instead of making this the task of the quantum communication protocol. So let me now say a little bit more what we require of this link layer. So we basically want that on a node A, a higher layer can say, create entanglement for me, and I want, say, a certain number of pairs or a certain rate. I require this entanglement to have a minimum fidelity, so a minimum quality, and I'm happy to wait for a certain amount of time. Of course, like I said, at some point we will hopefully succeed in producing entanglement and return to the higher layer an entanglement ID, a qubit ID, and a fidelity estimate. So why am I bringing up this entanglement ID, and why is it important here? Remember earlier I said that one of the challenges, in fact, for computer science challenges to design such protocols is to mitigate the inherent physical imperfections of quantum devices. And quantum devices have, I think for many, many years to come, the problem that quantum memory lifetimes are extremely limited. So when designing such protocols, it's useful to think, of course, also what we actually want to do with them. So what are the requirements that the applications in the end are bringing to this network? So we distinguish for the link layer protocol actually two use cases, or two types of use cases, one that really come from the applications and one that come from the network layer, meaning we want to produce long distance entanglement. So on the application side, one can classify quantum applications loosely into two types. One of them is what we call measure directly, meaning that as soon as the sender and receiver have managed to produce entanglement between them, they immediately measure it. An example of this, for example, is quantum key distribution. And here we typically produce many, many pairs, so millions of pairs of entanglement, and we measure them. So here it's important that because we measure it directly, and we don't need to store the entanglement at the end nodes, which also means that the jitter, so the time between producing one pair of entanglement and the next, does not matter very much, because we're not keeping this quantum information around. So if I make a million pairs, and there's somewhere a minute of gap in timing, that really doesn't matter. Some applications, which we like to call create and keep, actually only require very little entanglement, say only 10 pairs of entangled qubits, but it's important that they are actually kept around. So they're kept at the end nodes, they're stored, and we can only proceed with the applications once we have produced, say, all 10 pairs of entanglement. Here, jitter is now actually very important, because if there's a 1 minute gap producing one pair of entanglement to the next, this actually means that I need a quantum memory at the end nodes that can store the entirety of the entanglement for at least 1 minute. So in that sense, it's a little bit more similar to real-time traffic, for example, with real-time constraints in a classical network, for example, video, we don't want to wait between one piece of the data and the next. To our link layer protocols, we also talk about a network layer use case, which you also like to call create and keep, which is essentially facilitating long-distance entanglement generation using this process of entanglement generation, actually having a memory at the midpoint where we then perform operations. So there's some of these, even if you don't understand physics and you want to design such protocols, it's useful to be aware of some facts about such physical devices that bring some design considerations to the table. For example, you may be asking, well, if I want to produce entanglement between using this midpoint with the detectors that we saw in this video, maybe I can just go and shine my laser on one node all the time. And if the other node is also ready to produce entanglement with me, then in that case, I also shine the laser there. So, that might be a priori a good idea, but it is actually the case that this process of triggering entanglement generation induces noise to the entanglement that you already have in the storage qubit. So this actually means that you want to avoid triggering, so asking the nodes to produce entanglement, unless both of the nodes actually already agree. So we only trigger at the same time in order to not destroy the qubits, the entanglement that we already have. The second point, as already mentioned before, quantum memory lifetimes are extremely limited. This means that we want to minimize waiting at all costs as soon as the entanglement has actually been produced. And this means that in quantum network protocols, prior discussion, so a prior agreement, is often preferred. And this is somewhat different than in classical networking, where sometimes it's a good idea to just run ahead and then later try and recover. But here we want to set up sort of an agreement ahead of time. So I've already mentioned, I hope at least before we're disconnected, that we don't need to deliver perfect entanglement to the application. Actually, we don't need to perform really quantum error correction to eliminate all the errors. So we don't do quantum error correction for that. But you may be saying, hey, maybe I want to have at least some quality assurance about the kind of entanglement that I'm producing. Can I maybe use a form of error detection, say a quantum CRC? And the answer to that, there's actually two answers to that. Namely, on paper, the answer to that is yes. On paper, we can, of course, use quantum error correction to perform quantum error detection. And we could have a quantum CRC in that way. So the reason why we don't really want to do that, at least in our protocol, is because quantum error correction requires the manipulation of many qubits at the same time. And that is technologically a very hard problem. So the way that we actually deal with sort of a quality assurance is that instead of using a quantum CRC, we sometimes intersperse test grounds. So we sometimes produce entanglement, not for the purpose of delivering it to any higher layer, but just for checking basically whether everything is working correctly. And then one can prove a little theorem that actually says that, well, from these checks, we can infer something also about the entanglement that is not tested, namely the actual entanglement that we want to produce, for example, for sending data qubits. So I don't have so much time to go into the details of this protocol. I just want to give you a little bit of an idea. So basically, we have a higher layer, for example, a network layer application. We want to produce some entanglement, say create. And the first thing that the link layer will do is to form agreement with a remote node. So we add that in sort of a distributed queue. There's many other things happening, of course, in such a protocol, but I'm not going to go into it now. But given that we've done this, we can also try and schedule requests. We can, of course, have higher priority requests, but also our link layer protocol supports specific use cases, for example, measure directly or create and keep, which you can treat differently. So if you remember the little video on entanglement generation, you see that we shine a laser on both qubits, both endpoints at the same time. The qubits are traveling to this midpoint where we measure them to produce entanglement. So this means that at the physical layer, we really require tight timing synchronization, but at least we have decided to keep all the timing synchronization at the physical layer. The physical layer has very stringent timing demands, which means that the physical layer is actually going to initiate. So we'll pull the link layer saying, hey, should I be triggering entanglement generation in this specific time slot? Link layer says yes or no. We make an attempt to produce entanglement. The physical layer will tell the link layer, well, that attempt was successful. If the attempt was not successful, we're just going to try again in the next round. And the link layer is robust in the sense that it will actually sort of keep trying, at least for some amount of time, to produce entanglement, and then say, okay, okay, higher layer, I've produced entanglement for you. So evidently this is a bit of a cartoon, but I hope it gives you a little bit of an idea. One can then ask all kinds of interesting computer science questions. So for example, how should one schedule at all, or different types of requests? One can investigate such things if you want to play around with your own protocols, for example, using a simulation tool called NetSQUID, where we can actually not only implement these control protocols, but also model actually underlying quantum hardware and therefore explore the interplay between such control protocols and the physical hardware. So for this specific link layer protocol, we've done an extensive simulation investigation using actually longer runs to actually explore also how robust the protocol is in terms of various failures, short runs to explore trade-offs between the performance metrics that we've put forward, and also to explore scheduling. So I can't really talk about this in depth now, but for example, we've considered a simulation example, which is this link between Delft and The Hague. And in the simulation, one of course first wants to check, does this have anything to do with reality? And so we validated the simulation against the hardware in the lab. And then one can explore a few things. And I cannot show you very much, but for example, one thing that we would like to see from our network protocol, or maybe from your network protocols in the future, is how do these different performance metrics trade off against each other? So classically, I'm sure you're very used to seeing plots that, for example, what is the trade-off between throughput and latency? And one thing that we're particularly interested here is what is the trade-off between the standard quality metrics like throughput and the quality of the entanglement produced, meaning the fidelity. And in the physical devices, actually, we can get a trade-off between these parameters. So here, actually, we have a few lines for these different types of requests, so create and keep and measure directly. And for example, if you look at the right-hand plot, we can see the trade-off between the throughput, so the number of entangled pairs per second, to the fidelity. So larger fidelity means better quality. And you can see that if we ask for a better quality entanglement, so higher fidelity, the throughput, the number of pairs that we produce per second also decreases. So this is maybe something that you would intuitively expect, of course, at higher quality. Asks you to go a bit slower. But so this is the kind of trade-off that we're interested in understanding these protocols. So if you want to learn more about that, we actually perform the function allocation of a quantum network block. We explore quantum design considerations that impact such protocols and actual use cases. We propose a physically linked layer protocols, and we do a performance evaluation and also an investigation of how different scheduling strategies perform. So the question is, of course, where do we want to go from here? And maybe you also wanted to take part in this adventure that we are currently undertaking. So there's actually many challenges into computer science that come from designing quantum networks. It's not just about physics. And the first one is actually that we really want a fast and reactive control plane for producing entanglement. And that's extremely important because remember that quantum lifetimes are extremely limited. So this means that we want to design protocols in such a way that we need to store qubits for as little time as possible. You don't just want to do that point-to-point, but also in a multi-user network, somewhat related to that, also understand how we can actually route entanglement in such a network. We want to do a little bit more than quantum key distribution, which means that we need to think about how do we actually program quantum network applications. And that's somewhat different to just, in unquote, just programming a quantum computer, because it requires a close interplay between the classical communication between the sender and the receiver and the quantum programs that are being run on the quantum processor. So somewhat related to that is, of course, also how do we optimize for that. Also sort of a different question is how do we schedule entanglement requests in a good way? And that is important actually not just to perform long-distance entanglement generation in the network, which requires all kinds of timing coordination, but also, for example, what is a good architecture or a good design to schedule also on the device itself. So we currently use the same device as the CPU, if you wish, as the quantum processor, and as the network device. And it cannot be both CPU and the network device at the same time. You want to understand also more about actually what are the requirements for quantum applications, and there's many more questions. So if you want to become engaged in it, you want to learn more, but you may be saying, hey, I don't have my own hardware at home, but I want to explore such things. If you're interested in trying to get a feel for how to program actually quantum applications, and you don't have this fancy hardware at the bottom, there's actually a little program that you can install on different classical computers that in the background will generate a quantum network for you. You can get a feel for actually programming such a distributed simulated network. So that can be quite fun. If you're interested in really exploring control protocols, we also have a simulator which is a discrete event simulator that does not run in real time and give you so much nice feel of actually really running in real time quantum network applications, but it does allow you to explore, of course, on the physical layer what are good designs for quantum devices, but also to study ideas for different control protocols and also what is the performance of different applications in such a network. If you want to learn more about quantum crypto, maybe you also are interested in the MOOC that we have called QCryptoX on edX. And if you want to read even more, there's all kinds of links you can look up later on this slide when you pause the video. If you want to learn more about the Quantum Internet Alliance, you can go to this URL and also get in touch with all kinds of people in academia and industry across Europe. So thank you very much, and also thank you for your patience after these technical interruptions. And if you're interested in becoming involved in our efforts here in Delft, please feel free to contact me or see our website below. Thank you very much.
Thank you, Stephanie, both for the wonderful talk and for your patience with the technical difficulties. I know that we have received a lot of questions, probably over 100 different questions, all on different aspects. And I've done my best to try and distill these down into a few that we can cover in the last few moments. The first question from the audience relates to the physics behind quantum networking. And it raises the point that entanglement establishes correlation, but that might seem to violate the speed of light. And I was hoping that you could talk a little bit about how entanglement and its role in networking continues to satisfy that relationship with the speed.
Yeah. Yeah, so I think that's a really excellent question. So first of all, I think it's important to understand that coordination is not the same as communication. And maybe I'll give just a little bit of an example. Let's say that we want to coordinate our actions. We've been arrested by the police, and they ask us, what have you been doing at 8 p.m.? So that's an example where actually it would not be important, really, maybe what we say, but it is very important that we coordinate, that we say the same thing. So if I say, I've been eating pizza at 8, and you say, we've been eating pizza at 8, then that is an example of coordination, where we actually sort of give the same reply, even though it does a priori not mean that we have to give the same reply. If we both say we eat ice cream at 8, it also works. So communication is a way to achieve coordination. Namely, in this case, if we would have been able to talk to each other, we could have said, we've both been eating pizza. But coordination can also exist in the absence of coordination. And this is actually sort of what entanglement achieves. So in a sense, entanglement allows us to perform better in situations where we both say receive a challenge, so where have you been at 8 p.m., for example, where we instantaneously want to give an answer without any extra communication. So here the answer is not determined ahead of time, but we can use entanglement to coordinate on what we say. I'm not sure whether this analogy maybe gives some intuition, I hope.
Wonderful. No, thank you. The concept of entanglement, of course, is always difficult to wrap our heads around. And you discussed that concept, especially with the examples of two-party communication. But there were several questions asking, how does entanglement scale up? When you start looking at more complicated networks, I think you had a few pictures in there showing branches and these types of designs. And I was wondering if you could say a few more about comments about that.
So I think it's important to specify exactly what it means to scale up entanglement. So it's a little bit of a shame that I cannot back ask the question to clarify the question, so I'll try and make the best of it. Scaling up, I guess, could mean several things. One of them could mean that we try to produce entanglement faster. We try to, between the sender and receiver, have more pairs of entanglement at the same time. Or it could also mean that maybe you want to generate some sort of multi-parted entanglement between many people at once. And these, of course, are many different very different questions. So maybe with respect to scaling up in the sense of being very fast. So one should understand that we cannot yet have large distance quantum networks. So our objective is for the moment to produce entanglement at a horribly low rate. So we are currently in the basic step where we really are happy to make that work. And if we had a quantum network that it would allow all users to produce entanglement at 1 Hertz, we would already, for the moment, call it a success. Scaling up with respect to how much entanglement can I hold at the same time, say how much entanglement can simultaneously exist between the sender and the receiver. So if you mean that by scaling up, that would mean that the sender and receiver needs to have a larger quantum processor, so more qubits at the same time. So quantum processors currently don't have so many qubits at the same time. And remember, what we're asking here is actually not just a quantum processor, but a quantum processor that can store the entanglement for preferably minutes. So we can run a useful protocol. So people here in the lab have achieved roughly 20 qubits in networkable quantum devices, where some of them can be kept for minutes. But one should realize that the path towards sort of making these end nodes more powerful and having very many qubits is also a very difficult one. So there's a third.
Yeah. I was just going to build off that question. You mentioned the intersection between the quantum processors and the networking, and I guess I was curious how you saw the developments going on in quantum computing and the developments going on in quantum networking. Are they aligned up to complement each other well, or does there need to be more coordination in that area? I think you get the sense.
Yeah. So it depends a little bit on maybe where. So we at QTech work together as a very large team of people in the roadmap of quantum internet network computing. So in the network division of QTech. And we actually do quantum networks both at short and at long distances. Short, meaning that we try to build a quantum computing cluster where we want to connect many, where the objective is actually to do more computing. And long distance, of course, is to do more communication style tasks. So I think there's a huge amount of synergies actually between building advanced quantum networks and performing quantum computation. And my hope would also be that these fields get a little bit closer together. So, of course, there's many paths to success in quantum computing, but my purely personal opinion is that if one really wants to build a scalable quantum computer, one has to go modular at some point. It will not be, in my view, be possible, I think, to make one monolithic big quantum computing chip that can handle thousands of qubits. Instead, I think one will have several quantum computing chips which are actually interconnected in order to form one more powerful processor. I'm not sure whether that answers the question.
Well, I think that's an excellent answer, and I appreciate you taking time to stay after and answer some few questions today. Unfortunately, we've run out of time to go through our entire list of 100 or so questions. I want to thank, of course, the audience for participating in the question and answer session as well. Stephanie, I'd like to thank you again for your presentation. It was incredibly informative and very useful for everyone here. On behalf of the ACM and Stephanie and myself, Travis Humble, I'd like to thank everyone again for joining us today, working through the technical difficulties, and I hope you will join us again in the future for ACM Tech Talks. This concludes today's presentation.
Yeah, so thanks everyone for coming. For everyone who's maybe frustrated now that I haven't been able to answer your question, please feel free to drop me a line or DM me on Twitter. And I'm not sure that I can answer all questions, but I'll try and make an effort. Yeah, thank you all for coming.